Okay. So, since we have understood how to sketch the probability distribution function, how to sketch the probability density function, what probability density function and distribution functions mean, we would be interested in some statistics of a random variable based upon what we know about the density function. So, often we are interested in statistics such as mean, the variance and so on and so forth. So, let us basically define these things, right, understand what they mean. The mean of a random variable capital X with a probability mass function PMF P of x is denoted as E of capital X given by, so the mean is expectation of the random variable x given by this quantity summation over all I ui times the probability mass function of ui. That is, these ui's are basically possible values of the random variable x. So, ui's are the possible values of the random variable x, and you are looking at the statistical mean over all these possible values of the random variable x. So, this is given by this quantity, right. It's weighing the possible value with the probability mass function associated with this variable, that is what this quantity is, and then you average it. Now, the variance of a random variable x indicates the spread of the probability mass function of the random variable x. So, I mean, this is often interesting because I think people like the mean and the variance I think mainly from the Gaussian random variable. Assume that Gaussian distributions are called normal distributions, and for Gaussian distributions it is enough if we know the mean and the variance, and you can characterize the probability density function, right. And from that standpoint of view, people like to look at the two statistical quantities, which is mean and variance. So, mean tells you what is the average, statistical average, and variance tells you what is the spread in the probability mass function for the random variable. And but this does not mean that these are the only two statistical quantities of interest. Most for most practical purposes, from data collection that you see from census and other things, and if the population follows a certain normal distribution, then these two statistical quantities would be useful. Now, what is this variance? Now, variance is the expectation of the quantity x. So, you have the random variable, you subtract the mean from it, and then you compute you square that quantity, and then you take the statistical expectation, and that is what you get for variance, right. And this quantity is given by sigma x square, and sigma x is the standard deviation, and it is given by square root of the variance of x. Okay. Now, for the discrete random variable, you have a mass function, and then you can take a statistical average, and you can get the expectation in this form through a summation. For continuous random variables, the expectation is in the form of an integral. So, since this slide is all about discrete random variable, I think I have to mention this for clarity, that this is for discrete random variables because we have defined the probability mass function for this. Let us note the following. For a continuous random variable, expectation of the random variable x is given by the integral of x times the density function of x integrated over some region R if the integral exists, okay, and this has to be a small x to be careful. So, the expectation of a continuous random variable x is given by this integral x times the density, small x times the density of the random variable x, and if the integral exists, then you can compute the expectation. And one other important property that you need to know is expectation is a linear operation. You can prove this. I will leave this as an exercise, sort of straightforward. So, if I give you a mixture of a function of random variable, let us say we have a times some g of x plus b times h of x plus c. This is some mixture, and if I have to compute the expectation, I can do this as a times expected value of g of x plus b times expected value of h of x plus expectation of a constant is a constant. So, you can write it like this. So, this is an important result. It is a linear operation, but it is a very straightforward and a trivial result that you can easily prove this. So, as I mentioned to you, people are often interested in mean and variance thinking about Gaussian distributions, and people like to fit Gaussian distributions because it is sort of a normal distribution. Now, there are very interesting properties from central limit theorem, etc. I am not going to delve any of these in this basic background on probability because it is part of a separate course in itself. But it is not necessary that you have to compute mean and variance and they are enough to characterize the density function, right. You can calculate higher moments. So, one can compute higher moments, which is basically expectation of x power k. For different values of k, and then use these statistical quantities as appropriate for your calculations. So, I will leave this as additional material for your reading. You can look into Stark and Woods or any other basic book on probability, Sheldon Ross, etc. So, I would like you to read through the material on characteristic functions and moment generating functions to further your understanding on basic probability. So, and moments are particularly useful when we have to consider characterizing the PDF from observed data, etc. Okay. Now, let us look at some other statistical quantities and define these. if x and y are random variables with finite second moments, right, then we can define the following. One is the correlation, which is given by expected value of x y, and this quantity for continuous density functions can be written as follows. It is minus infinity to plus infinity x y times f x y x y dx dy. So, this is small x and small y. That means I look at the joint of x and y and I look at the expectation of the joint of x and y over the joint probability density function of x and y. Covariance is given by, is denoted by cov of x comma y. So, covariance basically you have to compute essentially the correlation, but by subtracting the bias from the random variables x and y. So, this quantity is basically expected value of x minus mu x and y minus mu y. So, basically subtract the bias, which is mu x and mu y, from the random variables x and y, and then you compute the correlation for this quantity, and you can evaluate and simplify this as expected value of x y minus expected value of x times expected value of y. Of course, you have to use the property that expectation is linear and arrive at this result. And along with this set of quantities, one of the important quantities is the correlation coefficient, and correlation coefficient between x and y is given by the covariance of x and y upon the square root of the variance of x times variance of y. So, these quantities tell you how linearly random variables x and y are related, right. I mean, this is one of the important metrics, and this is the physical meaning for this quantity, and people often compute these quantities for various statistical purposes. So, a few things to note. First, if either x or y has 0 mean, then expected value of x y is basically the covariance between x and y. Random variables x and y are uncorrelated if the covariance between x and y equals 0, and which also means that the correlation coefficient between x and y is 0. This is a very important thing. When you talk about correlation, you are looking at how linearly x and varies with y, right, and if they are uncorrelated, covariance of x and y is 0. There is another notion of independence, and we will see this. So, if and what is the link between independence and correlation? If x and y are independent, then expected value of x y is expectation of x times expectation of y. Now, this implies So, if expectation of x y is expectation of x times expectation of y, then covariance between x and y is 0, which means x and y are uncorrelated. So, if two random variables are independent, this implies they are uncorrelated. The converse is not true. That is, uncorrelated ness does not imply statistical independence. Okay, we will see an example to clarify this idea, and then we will get on to the next concept. So, we were discussing several properties and on probability etc., running through the basics of probability and random processes. So, let us work out an example and investigate if uncorrelatedness leads to independence, or what can we say about independence and correlatedness of random variables. So, let us consider an example. Consider two random variables x and y with joint probability mass function as shown below. So, I will populate a table what x and y can take. So, this random variable x can take x equals -1, it can take x equals 0, it can take x equals 1, y can take y equals 0 and y equals 1. So, I will populate the entries for the probability measure on the joint of x and y. So, this is populated as follows. A quick inspection into this table will tell you that this mass sums to 1, because 1/3 plus 1/3 plus 1/3 is 1. So, therefore, this is indeed and all of them are greater than or equal to 0, all the entries are greater than or equal to 0. This is indeed a valid probability mass function. Now, let us investigate if x and y are independent. Okay, let us investigate if the random variables x and y are independent. Now, consider the mass function where x takes 0 and y takes 1, right, and this is basically this entry here shown in the green circle. So, probability that x takes 0 and y takes 1, reading off from the table, this is 0. Okay. Now, they are independent if the joint mass function factorizes as this quantity here, that is probability that x takes 0 and probability that y takes 1. Okay. Now, let us compute the probability that x takes 0. Probability that x takes 0 is basically this quantity you marginalize over all y, right. If I have to write down the steps, it is probability that x equals 0 over all y, and then if you just sum this over this second column you get this as 1 by 3, and the probability that y takes 1 is the summation over all x, that is you marginalize over this row here, right. So, this is probability that over all x y taking a value 1, and then if you add the entries in this row, that is the second row, you get this quantity as 2/3. Now, just examine this equation. Probability that x takes 0 and y takes 1 is 0, which is not equal to probability that x takes 0 and probability that y takes 1, which is basically 2 nines here, right. This evaluates to 2 nines and this is not equal to 0. So, therefore, clearly random variables x and y are not statistically independent. Now, let us examine if they are correlated, right, for which we have to bring in these expectations. Let us examine if they are correlated. Now, consider the covariance of x y. This can be written as expectation of x y minus expectation of x times expectation of y. So, we need to compute these quantities. So, let us first compute expectation of x, right. So, expectation of x is basically the statistical average for this random variable x. So, x takes values -1, 0 and 1. So, -1 with a probability 1 by 3, and how can you get this probability? By basically marginalizing. Then it takes 1 with a probability 1/3 and it takes 0 with a probability 1/3, and this evaluates to 0. So, therefore, the second term in this covariance quantity is 0 because one of the terms is evaluating to 0. Let us compute expectation of x y. So, this is basically this has to be computed over the joint probability mass function of x and y. So, now reading off from this table. So, there are only 3 entries that are non-zero. So, let us take those quantities. So, x can take -1 and y can take +1, and the joint probability mass function is 1/3. Then x can take 0, y can take 0, the mass is 1 by 3, and x can take 1 and y can take 1, and the joint probability mass function is 1/3. So, this evaluates to 0. So, both of these quantities, that is expectation of x y is 0 and E x happens to be 0. We do not have to evaluate E y because one of them is heading to 0. Therefore, covariance of x y equals 0. This implies the random variables x and y are uncorrelated, right. Now, they are uncorrelated. This does not mean, so as we see they are uncorrelated, that does not imply that random variables x and y are statistically independent. Okay. So, this sort of clarifies the ideas behind correlatedness and statistical independence. Orthogonal random variables if expected value of x y equals 0, this implies random variables are orthogonal. Remember from the basics in linear algebra, right? I mean, this is basically some measure of an inner product, right? If you look at the inner product of two vectors, then if it evaluates the dot product is 0, then we say the vectors are orthogonal. In the statistical sense, if you look at the expected value of x y, x times y, expected value of x times y, and that if it evaluates to 0, then we say that the random variables are orthogonal. Now, covariance of x y equals 0 implies that the random variables are uncorrelated. Now, when either expectation of x or expectation of y are 0 and x and y are orthogonal. If x and y are orthogonal, then expected value of x y is 0. Then covariance of x y, which is given by expected value of x y minus expected value of x times expected value of y, this evaluates to 0. That is, if one of x and y have 0 mean and expected value of x y, the correlation between x and y, if that evaluates to 0, then basically the covariance is 0. So, therefore, for 0 mean random variables, orthogonality implies uncorrelatedness. So, if you consider 0 mean, if one of the random variables is 0 mean, right, then if the two random variables are orthogonal, that implies they are uncorrelated. So, these are some basics of probability. Of course, this is an entire semester course. I am just sort of squeezing this into about one hour plus lecture, so that you can get some basics sort of refreshed. I advise you to look into the texts that deal with probability theory extensively, and to go through these details carefully, so that you are sort of familiar if you are not familiar. But these concepts basically help you sail through the rest of the course whenever we deal with such statistical quantities. Okay, so we complete this.